So today we are going to be talking about quantum computing. Again, if you are following along on Twitch and you want the notes, just like Tyrion put in exclamation mark notes, we'll give you those. If you are following on YouTubers, the links for all that will be in the description. By the way, whatever medium you're following on, you should probably just subscribe to me on YouTube. It just makes a lot of sense. I do some original stuff. I tried like a joke video the other week. Kind of bombed. But it's all right. I don't mind. It was pretty bad. But I had a lot of fun with it. So, that's all that matters. Last time, which was a while ago, we did part 7, and we talked about the Stern-Gerlach machine. That was a while ago. That's one of my favorite ones. I feel like I peaked at this one and then didn't have to do anymore, right? That's the... I was like, once I did Stern-Gerlach, I'm done. But there's more to it than that. We should actually, keep going. And the Stern-Gerlach is just so interesting because then you can talk about how, swaths of particles come out of the oven, and then they get oriented in a certain direction. They get measured in that direction. We can talk about the superposition of both spin up and spin down and what that means. And how that, plays out quantum mechanically. It is nice because a quantum computer gives you a nice, a Stern-Gerlach machine gives you a nice quantum computer setup, right? We have a nice, easy up and down state, which you could assign to a qubit of like 1, 0 over 0, 1 and do all sorts of interesting physics with. But there is some question about whether or not fundamentally that still works. Experimentally, theoretically, everything looks this way, but there's still some question up in the air about how, about some of the more, fundamental philosophical and physical constraints of the Stern-Gerlach machine as it would be applied to a quantum computer. But nevertheless, that's not our story to discuss or to look into. We're looking into now the linear algebra that you need for quantum mechanics. So, let's talk about linear algebra. Linear algebra. So quantum mechanics is interesting, and I've told this story a few times, but it's just my idea of how quantum mechanics works at the level of like a first-year undergraduate, right? And it's learning a language. It's most fourth-year undergraduates who are experiencing their first quantum mechanical course won't be struggling on the math. Most will be struggling on understanding the language of quantum mechanics because many of those students have taken linear algebra. They've seen vectors, they've seen three-dimensional vectors, they've seen higher dimensional vectors. It's not the math that's usually the struggle. It's understanding how to interpret the language. So for us, we're going to talk about that today. So the math is, similar to probability theory, similar to linear algebra. I took both of those before I took my first quantum mechanics course, and quantum mechanics 1 was actually very difficult. I felt like quantum mechanics 2 was a lot easier because I had already learned how to speak the language, and then it was just applying it to a bunch of different problems. But quantum mechanics felt harder because it was actually trying to learn said language. And one of the tools that we're going to use is a vector space. So we can consider a vector to be a list of numbers that has some certain properties to it. We're going to be kind of in the realm of vector spaces, where a vector is a descriptor, where like the vector itself is a description of a particle, and we're going to be talking about that quantum mechanically. But you could consider like your three-dimensional plane, with z, y, and x. Have some point in that plane, and that point is going to have x, x, y, and z points, and then how do you describe that? Well, you describe that as some, I don't know what math people use, R vector? I don't know. Is R vector okay? I'm confused. Does it say less time on the board? It does. It does. It says less time. Less time. Just making sure for my notes, right? Come on. So we could talk about the R vector being a linear combination of every single point associated with its, its unit vector. And that would be like xi hat plus, y j hat plus z k hat. So this is a vector that you might learn about, And we could describe this as two vectors, one being, x, x, y, and z, and the other being I hat, j hat, and k hat. So this is just, something you might learn in Calculus 3 or something, or Calculus 2 even, or 1, or Algebra, something. Something somewhere you might have learned this, which is good, I hope. So what does that mean for a vector space? Well, a vector space is just a space of vectors, right? And I've also said this a couple times in the past, that, like, people don't really describe to you what a space is. Like, we talk about spaces in your calculus classes and your algebra classes and stuff like that. But physicists come along and are like, okay, we're going to consider a Hilbert space. And you're like, all right, I don't know what a Hilbert space is. Is it like a normal XY graph? And they're like, kinda, except it's infinitely big and it's made up of things that are, that you could, like, write in. Or it could be a space of 2 things. It could be a space of 4 things. It could be literally a space of how many ever things you want. And inside those things are vectors. A Hilbert space is a space of state vectors, I think, specifically. But really, spaces can just be whatever. You just have multiple ways of describing things, and you can then take those multiple ways of describing things and then map it into some arbitrary coordinate system and call that a space. So a vector space is literally that. It's just the space of all vectors, or a space of vectors relevant to a certain thing that we're interested in. So let's consider first a vector. We have to talk about the things that we can do to the vectors before we can figure out how to, and the things that we can do to the vectors, we'll change the vector space, we'll add, or we'll go to somewhere else in the vector space. We'll do these things algebraically. So first we could talk about addition. So if we wanted to talk about addition of vectors, we might have something like z1 down to zn. Of course, so for us, for our purposes, z's are anything in the complex number system, so it could be real or complex. Anything, a plus ib or whatever, it's like that's our realm for quantum mechanics, is in the complex plane, complex number system. So we could add up, like, 2 vectors, z1 and z1 prime. And what are we going to get? Well, we'll just, you're going to add up each individual element to itself, right? That's kind of the trick to addition in the vector space, and we'll get a sum of z1 plus z1 prime, and you can add them all up, and you'll get zn plus zn prime. And it's just, some vector addition. You add up the points as they go, at each element, add them up, you get that. Hey, Inversion, good to see you. So we can add vectors, and then we can, subtract them as well. But also, we can multiply by a scalar. So I guess maybe I'll just erase and start over. And multiplying by a scalar would be pretty much what you would imagine it to be, right? You're just going to multiply each individual. I guess if you've never seen this, you might have a hard time imagining. But you're going to multiply each individual element of that vector by the scalar. So for example, if we just have some scalar z, not my notation, just following the book, multiplied by some of these, by all of the elements of this vector that we've been considering, then you'd get exactly that. Z, Z1, ZZ2, ZZ3, all the way down to ZZ top. Jokes. Yeah, you just get ZZN at the bottom, right? And Schroeder scalar's coming next. And so this is just, some of the things you can do with the vectors that will come into play later on. So quantum mechanics notation for a vector, we normally, again, this is the language part, we normally have 2 things. We'll call them, this one we call a ket. I'm going to leave this in the video. And this one we call bra. Hi, Tropical. It's good to see you. It's always good to see you, Tropical. Thank you for coming. Is that a +1 or a -1? Oh, come on. Why do you say it's a -1? The only reason I made a ZZ Top joke is because Mandry's not here. Mandry would make it before me if he had the chance to. All right, so we have 2 types of vectors that we're going to talk about in quantum mechanics, and we're going to relabel them as kets. This one would be strictly associated with our column vector. This one is the complex conjugate. We're going to talk about more in a minute, but this is a bra. Okay, so we have bra, and you put them together, you get a bra ket. So yeah, so the bras and kets are kind of what we do, are kind of what we use when we talk about these vectors. Again, this is the vector itself is usually given by a ket, and then the complex conjugate is given by the bra. And we'll go into that in a little more detail in a second. Now, here's a note. Vector spaces do usually contain a zero vector that is different. This is a very common mix-up for a lot of undergraduates. This is different than the ground state, which is usually written as a zero. A zero in a vector is different. This doesn't have to be equal to zero, but this is usually associated with having a ground state. For quantum computing, it's associated with one of the bits. Usually we write the states as 0 or 1. But in a lot of oh no. Now I have to edit that out. Given by the bra, where the boob's coming from, I don't know. So the ground state is usually what we talk about when we talk about the lowest energy state. Oh man. Yes, it's a bra. This is a bra. Okay, so let's talk about a bunch of notation that we're going to use, okay? So I'm going to erase this so we can actually get this notation on the board. This notation is kind of relevant to quantum mechanics, and you're going to need all of it for like linear algebra stuff. It's very helpful, and this table is available in the book that we're using, which is Nielsen and Chang, and Quantum Computation and Quantum Information. I'm going to write it on the board, most of it at least, and maybe add a couple things to it at the end that are useful. So for instance, if we have our vector z, there exists a complex conjugate vector such that if we have z is equal to 1 plus I, then z star, the complex conjugate of z, is equal to 1 plus I complex conjugate, which is equal to 1 minus I. Basically, complex conjugate, you take the sign in front of the I and you change it from either plus to minus or minus to plus. Yes, there is pony merch. There is pony merch. Let's see here. Mech Bargains, thank you for the follow. Welcome, welcome. Alrighty, so next up we have, okay, so then, yeah, so this is the complex conjugate. Again, I mentioned the ket and the bra. Very, useful things when, oh, I wrote them wrong in my notes. If you are following along in the notes, you'll have to change that. How dare I? How dare I? Right, Tyrion? How dare I? Ket, bra. There we go. So if you're following along in the notes, you want to change that. Bras are uncomfortable. True. I think, I guess, from what I've been told. I don't know. I feel like people are fishing for clips right now and fishing successfully. Okay, so then we can talk about the inner product. An inner product is similar to a dot product, but not exactly. There's some differences. Inner products are really, like a dot product is like, everybody people have told me this before, that the dot product is like a simplification of an inner product. Inner product is what we talk about in mathematics. And I probably won't get into it right now, to be honest with you, because I didn't write a blurb about it. So I don't really want to go off of my notes and talk about something that I might screw up. But an inner product is going to be, let's see, so we have the inner product of these two states. We have a phi and a, ooh, I don't want to write a plus, and a psi. And, but the inner product, for all intents and purposes, is you're just going to be matching all of the elements with their associated vector, unit vector, or basis vector, which we're going to talk about in a little bit as well. And then the tensor product is, I like to think of the tensor product as kind of like combining a state. It's really multiplying every single, it's really multiplying like every single possible element by every other element, so it's kind of making a whole new bunch of elements. I also wrote it as one way to consider writing it, but they don't use it in this text, is like this. This is a more common way to see a tensor product between two states. You might think of something, well, okay, let's not get into the details of it. We're going to do this a lot in quantum computing. One thing that we're going to do a lot is if you tensor together two states, A and B, and A, is some qubit and B is some qubit, then you actually get four states because you have to consider all of the possibilities of each qubit. You have 0, 1, or 0, 0, 0, 1, 1, 0, and 1, 1. Each of these only has the possibility of being 0 or 1, but when you tensor them together, you consider every single possible combination of them. And then this is also, they also have it written down as this, which I've never seen before, but we're going to go with it when they do. So, and that's their version of a tensor product written like that. If you collect many tensor products, you have a tensor flow. I don't know. Unfortunately, a walk wins over Twitch for me now. Oh, very good. That's very promisingly. Good, good, good. Have a good walk. We'll be here, probably, when you get back. Unless your walk is very long. But enjoy your walk nonetheless. We'll just throw those on the floor. I don't need them. When you tensor flows when you sell and buy them. Good. Very good. And then lastly, we're going to talk about A, the matrix A. If there's a matrix, there also exists the complex conjugate. Complex conjugate. There also exists in the matrix A. So again, it's like taking every single complex number and changing the sign before the complex term. And then there's also a transpose of a matrix, which is literally taking a line through the diagonals and flipping the entire matrix. Transpose. I'll show you an example in a second. And then there's the big one, the most important one for us, the adjoint, or the Hermitian conjugate, as it's called sometimes, when you do both. So can we see an example of that? Sure we can. If you have the matrix A, B, C, D, and you want to adjoint it. Okay, so suppose you have that matrix A, B, C, D, and you want to adjoint it. Then again, for the complex conjugate, every single one of these is just going to have a star. For the transpose, you're going to draw a line through the center and flip it. So we'll have A star, C star, B star, and D star. And you can talk fancy mumbo jumbo if you want with if you establish all of the elements like that. So if you had if this was A, what is that? Seriously, it's just a truck? It sounded like a train. If you had some element of a matrix A, J, then the transpose is just going to be switching the elements. So if you transpose that, it's just going to be AJI. Okay? Good? Excellent? Some fancy mumbo jumbo. Wait, so we consider A star like Z star, we just switch the sign in front of the I. Yep. Looks very complex. Premier physics content. Premier physics content. Premier. Okay, so good. So then you just do that if you want to be fancy. Which the tensor notation stuff is really fun. Which we're not really getting into yet, but all these tensor identities that would get involved when you do matrices stuff is a lot of fun, but we're not going to touch any of that anytime soon. Probably we'll see some tensors in quantum mechanical language, but not for a while. Oh, we have one more rule to talk about. I don't have any more room, though. But I want to put it on this board because I have one thought, and the thought is to do all of this at once. So if we have a phi, we can do an inner product with a matrix in between, or an operator, I should say. Operator in between. To bras. You do bras for so long that you start to feel tenser than you did before. Okay, so if we have the inner product and there's an operator sandwiched in between. So this could be kind of interpreted two ways. You could talk about the inner product of the vector phi with A applied to psi, the state psi. Or you could talk about it as the vector, the inner product between A, adjoint? I think it's adjoint, yeah. Adjoint applied to phi with the vector psi. So basically this is to say that this is just an inner product, and A can either be applied to here, or you could apply A adjoint to here. Either way, you apply this to one of these states, and if you haven't taken quantum mechanics yet, you probably don't know exactly what that looks like, which we'll probably do eventually. Or I might have done it in the primer that's on YouTube, !YT if you want to check that out. And you apply this operator to one of the states, get some eigenvalues, right? Hashtag eigenvalues. And then the eigenvalues will come out because they're a scalar, and you'll just get the inner product between phi and psi. And whatever state comes after psi after you apply the operator to it. But again, if you haven't taken quantum mechanics, you might not know what any of that meant. If you have taken quantum mechanics, you know exactly what that meant. So, let's keep going. Now we got to talk about basis, because all of this is going to be about basis. I might have missed it, but what are these vectors called in physics language? And this A. So A is an operator, and the psi is a state vector. It's just a vector. I kind of even just said it was a vector. Again, that primer video I had talked more about states, but the ket is literally just a vector that's usually associated with a column vector. And then the complex conjugate is just the other vector. So this is just the complex conjugate of this vector. Yeah, and then the vectors are usually called, the psi's are called states because they are descriptive of something. You know, like they could be, a vector could be a spin vector, and we're going to see that in the complex C2 group. But that's where our first example exists in C2, which is the complex space of two numbers. And I think. And we're going to talk about basis because ultimately when you're in quantum mechanics, basis matters. Basis matters for the type of measurements you take. It matters for the information you can get out of a system. It matters tremendously once you get into really complicated physics stuff because you're going to get different states that could mean different things in different bases. And but either way, so we can talk about the space where there's two elements on the complex plane, and there's two vectors that we're going to talk about, or two sets of vectors that we're going to talk about. The first one is relatively straightforward, where you just have a 1 and a 0. And then the second one, a V2 vector, or V2 state, is going to consist of, 0, 1. And this is an interesting set of vectors in a spanning set that spans this space, where you can actually write them as any linear combination of. So a spanning set is a way of describing a vector space by talking about a linear combination of the vectors inside of that space. So, for instance, if we have summing over all AI VI, we'll get the vector space. So for C2, it's easy because we're only going to have two of them, right? And the goal is to get we can write a vector space for C2. So let me say, for C2, boop, boop, then we get, the sum A1 V1 plus A2 V2. We can actually look at writing it out in the column vector forms for people who are maybe unfamiliar with this language of quantum mechanics and vectors and stuff like that, plus A2 in 0, 1. And now we combine the two principles that we learned at the beginning. This is kind of all to come full circle back around. We want to do the scalar multiplication as well as the addition. And here we'll get A1 times 1, that'll be A1. We'll get A2 times 1 here, that'll be A2. And we can add them together and we'll get this vector, which is the arbitrary vector in C2 space. Okay? That's the goal. But then we can also, here's the thing, is like this is kind of what's cool about this, is there's a second set of spanning vectors in this, right? A second set of spanning vectors might look something like this, where instead of V1 and V2 being just simple 1, 0, 0, 1, we could write another one, and this is what's called changing basis. If you guys notice, that might be like something similar to like a Pauli Z, vector, right? And there's another one square root of 2. This might be considered like the poly x, right? Where you have 1 over root 2 times 1, 1 over root 2 times 1 minus 1. Okay? And then what can happen here is if you were to add these together in a linear combination of the following, a1 plus a2 divided by the square root of 2 times v1 plus a1 minus a2 divided by the square root of 2 times, it did not break. v2, thank God. And then if we were to do this multiplication out like we did last time in addition, what would we get? Well, we'd still get a vector with one element up here, one element down here, so we have to figure out what those elements are. We'd get a1 plus a2 divided by root 2 times, oh wait, no, so that's, if we multiply by v1, we get one here, and we get one here. Wait a tick. I think I've done this wrong. I did do this wrong in the notes. It'd be 2. There we go. Cool. Cool, I did do that wrong. I dropped the root 2 in the notes. Anyways, and then a1 minus a2 over 2. Very good. And then down here we'd have a1 plus a2 over 2 minus a1 minus a2 over 2. And then this would, of course, simplify to just a1 over a2. Yeah, I think I mistakenly have a minus 1 over root 2 there in the notes, so you have to get out on your own. In some contexts, we call the basis of functions normal modes. A couple oscillators. Reference for, oh, kind of. Yeah, does basis have a big, a BS physics replacement term too? Functions normal modes. A couple oscillators. I don't know. We usually just call it basis. Is this how you talk about it in reference frame switch? I don't know about reference frame switch. It's more of like a mindset frame. Because you could be going from, go to the basis. Because you could be going from, like I said, the z basis to the x basis. So I guess like you're looking at the particle and the different, looking down at different angles. So I guess that could be considered a reference frame switch. Reference frame switch. But I don't necessarily think that it's exclusively that. Maybe it is. I always thought it was more like you look at it under a different lens, and you could get a different physics. Because I didn't want to, pigeonhole it into being a reference frame switch, but maybe that's all it is, and I'm overcomplicating it. And the last thing I have there in the notes that we can talk about is the linear dependence is a set of non-zero vectors. They are linearly dependent if, I dropped it again. So linear dependence is going to be a set of non-zero vectors such that if all of ai's are not equal to 0, then a1 v1, this is the state, plus a2 v2, v2, plus dot, 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 all the way to an vn equals 0. That's linear dependence. And then specifically what we want to talk about is linear independence, because linear independence is the set of basis vectors, right? So linear independence is when this is not true, when you add these together and it's not 0. You could have, every single vector space has a basis, basically it has a set of vectors that is linearly independent. But then, of course, there's probably ways to devise vector spaces. In fact, there's definitely ways to devise vector spaces that that have vectors which are linearly dependent. But this, like for instance, if we, well, I'm not going to get into the details of it. But yeah, so there is ways to make this, to make different vectors in a vector space linearly dependent. But there is at least one set of linearly independent vectors in a vector space, and all of the linear independent vectors are called bases. So, or sets of vectors are called bases. I think that's it for today, huh? Nice quick little lesson.